like lattice-based cryptography, its security depends on the lattice hard problems. So, okay. So this lattice-based, one of the motivation first is alternating options. So it gives us the one more option to create the public key cryptography and digital signature schemes. So this gives you alternative option. This is the first motivation. Second thing is strong hardness guarantee. Astai in his paper, his seminal paper, he has shown that this lattice-based cryptography, the security depends on the hardness in worst case, hardness of the this lattice hard problem in worst case. Generally the normal public key crypto systems, the security depends on the average case, hardness of the problem in average case. So this gives strong hardness guarantee. So the lattice-based cryptography gives strong hardness guarantee. Okay. Third one is efficient operations and parallelizable. So if you see in this part in lattice-based cryptography, the operations will be addition of multiplication, addition of matrices and matrix vector multiplication. So these kind of things will be there. So these operations are efficient and they are parallelizable. So that is the one, that is another one. So it can be made efficient also. Fourth one is there is no quantum algorithm yet. So tomorrow, suppose the quantum computers comes into reality, then all these RSA algorithm, ECC or AlGamal can be broken in few seconds. Because there is Peter Shor has given the algorithm, he has given the quantum algorithm to solve RSA hard problem and discrete logarithm problem. And this RSA crypto system and this AlGamal and ECC depends on these hardness problems. Okay, so till now there is no quantum algorithm to solve lattice hard problems. So lattice-based cryptography is safe from the quantum computers also. Okay. The fifth one is fully homomorphic encryption. So till now, most of the fully homomorphic schemes are based on lattice hard problems. So what is the fully homomorphic encryption? Is basically secure computations on encrypted data. So one can do the computations on encrypted data. Let's take one example. Let's take this one. Suppose I want to compute certain things on my data. So I have the data. I want the cloud to do some computations on my data. Okay. Now, so one thing is that since my data is some privacy is there, some secret, I have the secret data. I don't want to give the plain data to the cloud. Okay. And second thing is cloud does not want to give his algorithm to me, which computes which computes a certain function f. Okay. So he doesn't want to give his algorithm to me. So what to do? So there is a fully homomorphic encryption. In this case, what I can do is I can encrypt my data and give it to the cloud, and cloud will do computation on the encrypted data. Okay, and he will do the computation on encrypted data, and after that he will send that part that one to me. So what I'll get whatever I'll get. I'll decrypt it. After decryption, I'll get the computation on the data. So the output will be what I'll get is I'll get the computation on the data. Okay, so this is called fully homomorphic encryption. So in this case, I don't need to send the plain data. Similarly, cloud does not need to give his algorithm to me. Okay, so this is the one. This is called fully homomorphic encryption. Okay, so these are the things. So fully homomorphic encryptions, almost all the schemes are based on lattices. Okay. These are the positive motivations. So some negative is there. So in the lattice-based cryptography, the size of the ciphertext is very high. There is a ciphertext blow up. So for one bit of plain text, the size of the ciphertext is very high. So that is that is the problem here. Second one is the size of the public key is very large here, as you will see later on. So the size of the public key is very large. Okay, these are two negative things are there. Rest are positive. Okay. Okay. So now, what is the lattice? So you know the vector space. So it's similar to vector space only. In the vector space, is a set of is a linear combination of n linearly independent vectors. That is a vector space. You know that the definition. Here the lattice is little bit different. So it is here not the linear combination. Here it is as you can see here, lattice is set of integer linear combinations. So in the vector space case, it is the set of linear combination, but in the lattice is a set of integer linear combinations. So the linear combinations, the coefficients are only integers of n linearly independent vectors. So that is the lattice. Now let's take this example. Let's say the b1, b2, bn are bases. Okay, they are the bases. Okay. Now what is the lattice? So lattice is basically set of integer linear combination of these bases b1, b2, bn. And so if you see, the integer means is x1, x2, x3, xn has to be integer. Okay. So if they are real, then it will be a vector space. And the lattice, these are integers. Okay. Or since these are integers, so the lattice L equivalent definition you can give it. So lattice L is a set of points in n dimension with periodic structure. So obviously there will be a periodic structure because all these x1, x2, xn are integers. So let's take this example here. As you can see in the figure here. So let's take example of 2 dimension. Let's say v1, v2 are 2 vectors. Okay, so they are bases. They are bases. Okay, v1, v2. Now we can get the lattice as integer linear combination of these v1 and v2. v1 and v2. Okay, so you will see the set of points in n dimension with periodic structure. These things you will see. Okay, this is called lattice. Now if you see here, can you construct the same set of points from another set of bases? So obviously you can see 2v1 and 2v2 are also they are also independent. Okay, so b1, b2, so if you see the basis, it has to be independent. That is first step. So 2v1, 2v2 are independent. Now whether the 2v1, 2v2 will be basis if they can create, if their integer linear combination will be all these points. So can you create all these points from these 2v1 and 2v2? Anyone? So can you create this lattice from these two independent vectors, 2v1 and 2v2? We can't create, because you can see how do you create v1? We cannot create v1 as integer linear combination of 2v1 and 2v2. So in that case, you will have half. The b1 will be 1 by 2, half. But in the lattice, we need integer only. We need only integer. Okay. So this 2v1, 2v2 are linear vectors. Sorry, linear. They are linearly independent vectors, but they cannot be the basis of this lattice. Okay. So in the if you see in the vector space of 2 dimension, and if you take any two linearly independent vectors will be the basis. That is the in the vector space, you take any two linearly independent vectors will be basis. But that is not the case in the lattice. So any two linearly independent vectors may not be the basis in lattice. As in the vector space, it is true. Okay, that is the difference between the vector space and lattice. Okay, so this is the one. Okay, so this one what we have seen the lattice. Now we'll see. Okay, but there are many bases will be there. It's not like there will be only unique bases. Bases are not unique. They can be obtained from each other by integer transformation of determinant of. So you had a matrix whose determinant is +1 or -1. Multiply that one with the another basis. Like in this case, 1 0 and 0 1. This side 1 0 and 0 1. You multiply it, you will get another basis. So that is the one. So the basis is not unique. Although in this case, you see 2v1, 2v2 is not basis, but it is basis in the vector space. But in the lattice, there will be more than one basis, and you can get one basis. You can get the one basis from another basis by multiplying the matrix whose determinant is +1 or -1. So now you can see here this is this graph. So if you multiply this, you have the basis 1 0 and 0 1. So v1 is 1 0 and v2 is 0 1. You multiply this one with matrix 3 2 and 4 3, whose determinant is, you can see here, determinant is equal to 1. 3 9 -8 is 1, and if you multiply this one, you will get 3 2 and this 3 4 and 3 2 and 4 3. So you see this 3 2 1 2 3 3 2, this one, this point, and 4 3 4 3, this point. Okay, this 4 3. Okay, so this one. Now this is the one, another basis we got it. Okay, so this one. Now let's see some hard problems in lattice. So some well-known hard problems. So if I give you some arbitrary basis, now we'll see what is the arbitrary basis, not good basis. This and to find a point which is and you are given x, some point is given to you, and you have to find out a point which is closest to x. That is also a hard. Find a vector or a point in lattice L, which is the lattice which is in the L, and which is closest to x, is also a hard problem. Okay, so this is a hard problem. So you know the hard problem. So hard problems are basically problems. It's not like the hard problems cannot be solved. It can be solved, but it will take exponential time. It will take a lot of time. It will take many thousands of years. Okay, that is a hard problem. That is the meaning of hard problems. Okay. Now, similarly, another hard problem is that given an arbitrary basis for L, find a shortest vector in L is also a hard problem. Okay. So if I give you some arbitrary basis of L and I ask you to find a shortest vector in that L, that is also a hard problem. Okay, so that's all. These are some old lattice problems. Now we will see some modern which are used in the modern lattice-based cryptography. First one is small integer solution problem. Okay, SIS problem. Then you have IS problem. Okay, so given an integer q and matrix A of size n cross m. So matrix A of size n cross m and a real beta, and find a non-zero integer vector E of size m such that A is equal to 0. Okay, and this E is less than or equal to beta. That is also hard problem. So it's hard to find E such, or you can see this way. It's basically hard to find a short E such that A is equal to 0. So this is called SIS problem. Okay, so hard to find short E such that A is equal to 0. So short E means which are less than beta. Okay. Same IIS problem also. Now you, instead of 0, you will have U also. So you will have input will be U, A, matrix A and beta. Now you have to find out E such that AE is equal to U. So you have to find out sort E. Sort E basically means which is less than beta. So find a sort E such that AE is equal to U. So that is called IIS hard problem. So it's hard to find. If you want to find E such that A is equal to U and this E is less than beta, it will take many, it will take thousands of years. Okay, so these go. Okay, so okay. 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 So Babai has given a, although closest vertex algorithm problem, closest vertex problem is a hard problem. Okay, it cannot be solved in real time. But Babai has given one algorithm to solve this closest vertex algorithm. So in certain cases it will work. You see, certain cases it will work, and most of the time it will be a hard problem. Okay, it will take many years. So what is the Babai's closest vertex problem? So now we have given the lattice which has the basis V1, V2, Vn, and let's say WBA arbitrary vectors. Okay, and we have to find out a vector which is closest to this W. So W is not the lattice point. So it is a some point in real space. Okay, so you can say vector space. So W is not a lattice point. So what you have to find out? You have to find out a closest lattice. You have to find out a lattice point which is closest to this W. Okay, it's clear. So that is hard problem. If you are given the arbitrary basis, it's hard problem. Okay, so Babai has given this algorithm. It will work in certain basis. That we will see now. So what is the problem is, we are given W, which is a arbitrary vectors, which is not a lattice point, and we have to find out a lattice point which is closest to W. So I'll give you this example, maybe it will be more clear. Yeah. So let's say P. This is the P. Okay. So you are given this P, which is not lattice point. So you see the lattice point here. These are the, you can see first two bases. Okay, so these are two bases, and from this, if you do the integer linear combination of these two vector bases, we'll get all these points which are the lattice points. We'll get the lattice. Okay, these are lattice. Okay, so now in the lattice, if you see the P here, point P, you can see here green line, the bullet point. This is a arbitrary vector. This is not a lattice point. Now you have to find out a lattice point which is close to this P. Okay, and for that Babai has given the algorithm. Okay, so that's what you do. Okay, so what you have to do is first W you write as a not integer linear combination. So W is not a lattice point. Okay, so what you do is we write W as a, because V1, V2 and are anyway basis. So you write the linear combination of W, you can write as a linear combination of V1, V2, Vn. Similarly, if you take two dimension case, P we can write as a linear combination. So this is not integer linear combination, because that you can't write, because P is not a lattice point. You can't write an integer linear combination of these two V1, V2. You can't write P as an integer linear combination of these two vectors V1, V2. Okay, so what you can write is, you can write P as linear combination of these V1, V2. Is clear? So we'll write this part, vector space part. Okay, so that we write, but T1, now you can see T1, T2, Tn are real numbers. They are real numbers. Okay, now what Babai has given the algorithm, So what it is, you find the nearest integers to T1. So TAI computes AI. The TI is a real number. Now what you do is you find the nearest integer to this real number TI. So AI is nothing but AI is an integer which is nearest to this TI, real number TI. So suppose the TI is equal to 3.9, then AI will be 4. Okay. If TI is equal to 1.2, then AI will be 1. Okay, so nearest integer to TI. Once you get the nearest, once you get this AI, then what you do is you do the integer linear combination of B1, B2, Bn. That is this one, A1, B1 plus A2, V2, An, Bn. Obviously, this will be a lattice vector. This will be a lattice point because it is an integer linear combination of V1, V2, Bn. So this will be a lattice point, and this is the answer. So what Baba is saying that this will be the answer. Now you can see this algorithm will work for certain basis, not always. Always this will not give you the right answer. Okay, so it will work in certain basis, and certain basis it will not work. We'll see that now. Okay. Now the thing is, if the vectors in the basis are reasonably orthogonal to one another, so you have basis they are orthogonal. So orthogonal, the two vectors are orthogonal if their dot product is 0. So if you have the basis are reasonably orthogonal, okay, then the algorithm solves some version of, so then Baba's algorithm can solve the closest vector problem. So you can solve this, it will give the correct answer. But if the bases are highly non-orthogonal, they are not highly non-orthogonal, then the vector returned by the algorithm is generally far from the closest. So then it will, in this case, this Baba's closest vectors algorithm will not work. It will not give you the right answer. Clear? So it will not give you the right answer. Okay. So this is this one. Now let's see this part. So now let's see this. So now you can see these are the two bases. They are near to orthogonal. They are not completely orthogonal. You can see in the 2 dimensions they are not perpendicular, but they are near to orthogonal. So they are not highly non-orthogonal. So we want this one reasonably orthogonal. Okay. So these two are bases and they are reasonably orthogonal. They are near to perpendicular. Okay. So now if you see from this one and you apply this Baba's algorithm, you will get correct answer. So now let's say P is there. Now if you see this P, write this P as a linear combination of these two vectors. These two vectors. You can see here these two vectors. Okay. Sorry. These two vectors. And now in that one, the real numbers, as you can see this part, is AI, if TI converted into AI, which is integer. Once you convert it into integer, then it will be now integer combination of these two vectors. So integer combination of these two vectors. So that will be either this point or this point or this point or this point. In this case, it will be this point. So it will give the correct answer. You can see this part. If you calculate this one, you will get Q. So now you can see it gives the correct answer. So the lattice point which is closest to P is Q. Correct answer. So this Babai algorithm, if you have this basis, then it gives the correct answer. And these bases are called good bases. And these good bases are generally short bases also. So these are short, so the good, and they are near to orthogonal. So these three are synonyms in the lattice-based cryptography. So they are good basis, orthogonal basis, and short basis. So you see later also these good bases orthogonal and they will be short. Okay. this works in the this Babay's algorithm can compute the closest vector, closest lattice point to the arbitrary vector p. That will work. Now let's take another basis. Now I can take this highly non-orthogonal basis. So this you can see this vector. You can see this vector, and you can see the parallelogram using this vector will be this one. Okay. Now these are the arbitrary vectors, and you see this is highly non-orthogonal. So from these two vectors, you can create this lattice point. Okay, you can create the lattice point from these two vectors. Okay, they are bases. Now suppose we want to find out the lattice point to the vector arbitrary vector p. This is the p. We want to find the lattice vector. Okay, we want to find a lattice point which is closest to p. That we want to find out. For this, if the basis is this highly non-orthogonal basis. Now what you will do now? Now you can see, apply the, so first what you have to write? You have to write this p as a linear combination of these two basis vectors, highly non-orthogonal basis vectors. Okay, and then what you have to do is the real number you have to change into the nearest one, nearest integer. So what you will get? You will get one of the point of this parallelogram. So obviously you will get one of the point of this parallelogram. You can see, like previously, the answer was one of the point of this. When you convert real number into integer, so answer will be what? One of the point of this parallelogram. Luckily here you will get q. That is correct. But here you will have one of the point of the parallelogram. So now you have either this one, either this one or this one or this one or this one. So we'll get either this one of the point of this corner points of this parallelogram. Okay, that will be the answer. So what will be the answer now? It will get answer as q. But that is the wrong answer. You can see the nearest point, nearest lattice point to p is this one. Nearest point to p is this one. So this is the wrong answer. Okay. So what I am saying is that this Babai has given the algorithm, but that will work only one has the good basis, so, or short basis or orthogonal basis. If you have bad basis, this called highly non-orthogonal basis are called bad basis, then you cannot get the correct answer through Babai's algorithm. Okay, is clear this part? Any doubt till this point? Okay, so now how to create a crypto system from this bad basis or long basis. As you can see here, till now there is no algorithm to compute the good basis from the bad basis. Okay, so you can see here, if I give you this one, okay, you cannot create the good basis. That is a hard problem. Okay, that is a hard problem. Okay, now that is a hard problem. And so what the crypto system based on the lattice is like this one. So what you do is you make the bad basis as a public key. Bad basis means long basis, highly non-orthogonal basis as a public key, and your good basis as a private key. Good basis means short basis and nearly orthogonal basis as a private key. Okay, and now if you want to send me a confidential message, what you can do is you will have your good basis, and from this good basis you find your bad basis. That is easy. Already you have seen the method. You multiply with the unimodal matrix. Okay, from this good basis you find the bad basis. Clear? and the bad basis will be a public key and good basis will be a private key. Now you want to send me a confidential message. What you'll do is you'll have the message, and similarly I will have my good basis and bad basis. I'll have my private key as a good basis and public key as a bad basis. So my bad basis, you will be knowing my bad basis. You will be knowing my public key, that is the bad basis. So what you will do is you will have the message. You will encrypt the message using my public key, using my bad basis. And that ciphertext you will you will send it to me. Even the adversary also can intercept it. But since the adversary doesn't have the corresponding good basis, he cannot decrypt it. Okay, so only the person who knows corresponding good basis will be able to decrypt it. Okay, so I hope you know the basics of public key cryptography. Okay, so from these lattice-based cryptography, you can this lattice-based hard problem. This hard problem, you can easily construct the lattice-based cryptography, lattice-based public key cryptography. Okay, this is the way. This is the way. We'll see the one scheme based on this one, and we know that recovering the good basis from bad basis is hard. You can't. It will take many years. Is it clear? This much is clear. Any doubt? Yeah, briefly I have discussed the lattice-based cryptography. So if you have any basics, if you have any queries regarding this one, you can ask me now. Otherwise, I'll move to scheme. Any doubt? Okay, good. Okay, so there is a proposition. Let L be a lattice and take any basis V1, V2, Vn. Then F will be a fundamental domain of L, and then determinant of L will be volume of F, and that will be this will be maximum. So maximum volume will be V1, V2, Vn, which is the basis of L, short basis of L. So this is the one. So this you can see the volume is constant. Okay, and that will be less than V1 into V2 into Vn. Here, and the Hadamard ratio is determinant of L divided by V1, V2, Vn. So this V1, V2 is basically good basis. This is basically very good basis, orthogonal basis. Okay. So now this Hadamard ratio will be low, very low, very less than 1, very near to 0, when the bases are highly non-orthogonal, when the basis is bad basis. So when the basis is good basis, this Hadamard ratio will be 1, near to 1. So that you can think of. So I'm not going in detail on this one. Okay. So you can think of this way. Hadamard ratio will be, if it is near to 1, then the basis will be good basis. If it is near to 0, much less than the 1, then it will be a bad basis. So if you want to find out the bad basis from the good basis, this we have to check. How do you check that basis is the bad basis? This is the criteria Hadamard ratio. Using this one, we will check whether the basis is the bad basis or good basis. Okay. Okay. So now the algorithm, first public key crypto system, lattice-based public key crypto system, was given by the 3 cryptographers. The names are GGH. This is also called GGS crypto system. Okay. So same idea. So the key generation part, you choose a good basis. So good basis means short basis or near to orthogonal basis. So you choose good basis V1, V2, Vn, and then from this one you find out the bad basis. So I told you, if you want to find out the another basis, you choose a integer matrix U whose determinant is 1 or minus 1 and multiply this bad basis with this u. So this w also will be the basis that already you have seen. First, this is the theorem. So first also we have seen, if you want to find out another basis, what you can do is you can multiply that basis with unimodular matrix. The matrix whose determinant is 1, and the resultant basis, this w, will be the set of bad basis. W1, W2, W1 will be set of the bad basis. So no, it will be another basis. Now we have to see whether this w is the bad basis or not basis. That just now I told you. You have to find out the Hadamard ratio of w. You have to find the Hadamard ratio of the w. If the Hadamard ratio of w is much less than 1, then it will be a bad basis, and that will be a public key. Because we need, you have good basis, then we need public key as a bad basis, highly non-orthogonal basis, highly long basis. Okay, so all these are synonyms. So that we need it. And this is the way, multiply the matrix. If you get the resultant one has the very low Hadamard ratio value, much less than the 1, then that will be our bad basis, and that will be our public key. If it is near to 1, it means you have to choose another u. Then you choose another u till you get the basis whose Hadamard ratio is much less than the 1. So this is the way to get the key generation. You have to choose private key and public key. Yeah. Okay. Now we want to encrypt it. So now we want to encrypt it. So we have the message, in the public key cryptography system, if you want to encrypt, and what you need the message, and you need the receiver's public key, or you can say receiver's bad basis. Okay, you need receiver public key, or you can say receiver's bad basis. So you are given M, the message, and we will write this one in X1 in bit format and bits. Okay, so now this is given. Now we are given bad basis also. Okay, so bad basis is bad basis of the receiver. Let's say the bad basis of the receiver is W1, W2, Wn. Okay, so what you do is you find the dot product of M and the basis. So what you will get is X1 W1 plus X2 W2, and you get Xn Wn. This you will get it. Okay, this you got it from, if this you can, and W is known to the adversary also. W is the public key of the receiver, which is known to everyone. It is also known to the adversary. From, if you compute only this part, one can compute easily X1, X2, Xn. But now if I add some noise here, some small vector r, okay, if I add here r, then what will become? This is the lattice point X1 W1, because the X1, X2, Xn are either 0, 1, 0, 1, 0. They are not the real numbers. So if you do the integer linear combination of W1, W2, this is also a lattice point. Okay, this, so X1 W1 till X1 Wn, this is the lattice point. You can see this is the lattice point. You can see, you can say, if you get this is the, or you can say this any point, this you get. Let's say this Q you got it. Now from Q, or you can say we want this point. This, you can see this point. We got one lattice point, any lattice point. Now what you do is you add certain noise. You add this point, you got it, add R. So once you add R, you will get P point. So we'll get P here. Okay, so this will get it. So this P will get it. This P will get it. Q is there, X1 W1 plus X2 W2 plus Xn W1, you will get Q, and you add some little bit noise. So you'll get P. R is very small, so it should not be large. So you'll get You will get P now. Now this similarly here also you will get this point P. So what is this? You have the Q. You had you had this one, and you got P. Similarly also here Q was this you add P, you got this one. Okay. Now this is the ciphertext. E is the ciphertext. It is sent to the receiver. Okay. So now can you find the, basically you have to find out x1 w1 plus x2 w2 x and w1 from this E. So you can, I give you an example. This is known to you, this point is known to you. From this one you have to find out the nearest vector, this point. And this you can find if you know the good basis. I told you, if you know this point, you can find correct Q from this P, only you have good basis. If you have bad basis, like here, you have bad basis, you can't find this nearest latest point. You will get this Q, that is wrong answer. Okay, this one. So now apply Baba's algorithm and find the closest point V to E, that V will get it, and then you multiply W inverse, you will get X. This X, X1, X2, Xn, that will be recover N. This is the algorithm. Okay, this is the first lattice based cryptography, public key crypto system algorithm. You can see here. Is clear? I hope this is clear. Okay, any doubt to this point? Any questions? Okay, okay. So this is the first algorithm, and then this is the security approach. I'll see.
So can you repeat again?
Yeah.
The decryption part.
Decryption part.
Yes.
Yeah. So I have told you, you got this. I think. Can you see the pointer here? Something. I'm pointing something. That part is visible. Is it visible?
Yes, yes.
Yeah. Okay. So you see here the ciphertext E. What I am doing is here. I have the message x1, x2, xn. So a message m is there, and you have message m. It will be converted into n bits. So these are x1, x2, xn. They are bits. So let's say m equal to 1 0 0 0 1 1 1. So this x1, xn are bits. Now what you are doing is this x1, xn. I am dot product with this, multiplying with the w1, wn, bad basis. So when you are doing the bad basis with this one, what you will get till this point, you will get one a lattice point. This will be a lattice point like this one. You got this. These are the w1, w2 bad basis. If you do the integer linear combination of these one, you will get one of the point. Okay, one of the point. Okay, and now let's say you got a certain point, this one, and now you find out you add some noise. So you see this part. If this is in this part, if you get this point, the nearest one is this side. You add the R. If it is this point, then you add R. Small noise. This is called noise. You can't add that V1 by 2. It should not be. It should be less than V1 by 4. That you see. Okay. So you add a small noise R, and you will get this P point P. Okay. Like this one. This one. You suppose this is the Q. You got it. Add certain noise R. You will get P. This is the point. So your this ciphertext is the point P, and we want to decrypt it. And now the receiver has the good basis. Okay, so he has to find out the P, he has to find out the x1, x2, xn. So he has a good basis. He doesn't have he also has a bad basis, but he also has the good basis. So now you can see he has a good basis. Now this is the point ciphertext. P is the ciphertext C. Now using this good basis, He can get the point Q correctly. I told you from the good basis you can find the nearest lattice point to P. You can nearest lattice point Q to P. That you can get it. Okay, so we got the Q. That is the correct Q. If you are this is the basis, you can't get the nearest point. Okay, so other adversaries, they have the bad basis. I am the attacker. I know the receiver's public key, bad basis. From that bad basis, I can't find the point P. I'll get the wrong one. This one. I told you. Only with the good basis you can get the Q. So once you get the Q, the lattice point, these are. So we got Q. So Q is nothing but x1 w1 plus x2 w2 till xn w1. So this we got it. We have removed the R noise. This we got it. So basically we got it. This xw. Okay. Sorry, this mw. The matrix mw. Okay. Now you multiply w inverse. So this one is basically w inverse. So it's printing mistake here. So this is the E. So you got this part. The B is the lattice point. It's close to U. So what is the V basically? X1 W1 plus X2 W2 dot dot X and W1. That is the V. You multiply with the W inverse. So what you will get? You will get W inverse. You will get X. That is N. Okay. So this is the way. Clear? I hope it's clear. Okay. Okay.
Hello. Yes, sir, it's clear.
Okay. So this is the first crypto system. And now I'll come to this security approach later on. So maybe I'll see that because the time comes, we will see this part. Maybe in other classes, this may be over. So I'll see the modern. These are the old lattice-based crypto system. That is the GGX is the first lattice-based crypto system, and it is based on the lattice hard problem, like closest vector problem. Okay, and it is based on it. Now the modern lattice crypto systems are based on the another hard problems that is called learning with error, LWE. Okay, so all the you see fully homomorphic schemes, all the modern public key crypto systems, signature schemes, they are based on LWE or SIS or ISIS hard problem. So these three are the right now the hard problems based on which the lattice-based public key crypto systems are constructed. Okay, so let's see. So this was given. This LWE was given by the Regev, ordered Regev in 2005, I think 2005, roughly 2005 or 2008. Okay, so what is this hard problem? Now, if I give you some random linear equations, okay, so I'll give you some random linear equations on S. 4 variables are there. Let's take only 4 variables here: S1, S2, S3, S4, and I'll give you some, let's say 10 equations on this variable S1, S2, S3, 4 variables. Approximate equations, not equal. If it is this is equal, and I have 4 equations, then you know the Cramer's rule. You can easily compute S1, S2, S3. Okay, so it is approximate. So this part is maybe if the real this is equal to 7, and then it will be 8. It's the equal value is near to 8. Equal value is near to 16, like this one. So approximate random linear equations. If you have exact one, then easily one can solve. One can find out the S1, S2, S3, S4. Then you need only 4 equations on these variables S1, S2, S3, S4, and you can apply the Cramer's rule, and you can find the value of S1, S2. Here we don't have exact equations; we have approximate linear equations. Okay, Now this, to find S1, S2, S3, S4 is hard to find S1, S2, S3, 4 from these equations. That is a hard problem. Okay, so obviously if you have small, only four variables are there, then it is easy, one can easily solve. But if let's say you have Sn is there, so you have 2 to the power 9 variables are there. Okay, S1, S2, roughly Sn, the equations on 2 to the power 9 variables, and then you have arbitrary any number of equations, any number of approximate equations, random linear equations. To find S is a hard problem. That is a hard problem. Okay, is clear? So this, to find S is a hard problem. That is called search. So LWE has two versions, search version, and then you will see another one. So in this case, you are given, let's say you are given many equations on these 2 to the power 9 variables. So it's not only 4. If you do for 10 variables, 20 variables, then one, and you have the equations, many equations, one can easily find in polynomial time, and in feasible time one can find those variables. But if you have you have many equations on 2 to the power 9 variables, S1, S2, S3, S to the power 9. Okay, then if you want to find out these variables from these equations, to satisfy these equations, it will take many years. It will take thousands of years. Okay, so that is the LWE hard problem. Okay, clear? Now I'll give you the decision problem. So now this is another, there is search one, you have to find out. So now decision problems. Okay, you have to decide. Okay, you have to decide whether you say, and whether is computed using the proper formula or not. Okay, so let's see. Okay, so now you create a uniform vector A. Okay, Oracle who knows S is you know this variables. Okay, this S1, S2. Okay, now you create a matrix A, and then you find AS. Then you find AS. Okay, so you have A is public. This A vector is public. This is public. Okay, A vector is public. Then we are doing AS. So when you are doing AS, you got AS. That is this one. So A is the vector like 14, 15, 5, 2, or you can see if you want to have the matrix, then this will be the matrix. Okay, so let's say A, and you multiply with the S, S1, S2, S3, S4. So this we got it, this value got it. Now you add little bit noise, because we have to make approximate equation. We don't we don't want exact one. Exact one, anyone can in exact equations using Cramer's rule, one can solve, one can compute S1, S2, S3. So what you do is, we want approximate equation. Okay, so what do? You add some noise. Suppose this comes out to be 9, so you add some noise, or you can say 9 minus 1, you make it 8. Okay, and second one, if you get you choose a vector and you get, let's say 15, you add plus 1, 16. Okay, like this model of this, like this one. So you get these many, you choose A, generates AS, then you add E. So add E, basically what is E is from Gaussian distribution. You know Gaussian distributions, so it will give you the probability that it will give you the very low value with high probability, near to 0. Okay, that is the Gaussian, you know, bell shape. Okay, high value, it will give very low probability, near to negligible. Okay, so because we need noise, we need small. We should not add more noise here. It should not be. If it is more, then it will be wrong. So no one can do it. So we want some small noise, small value, addition or subtraction. Okay, and that you can do by adding e. E is taken from the Gaussian distribution, and Gaussian distribution, you know that you can choose the small value with very high probability, and you can choose higher value with very low probability. So we don't want a higher value. Okay, so the probability of choosing the higher value will be negligible here. Okay, this one, and this you repeat this for different value of a and e. So you same S1, you choose another a, multiply it, you will get another equation. Then you choose another e, another equation. So you will get so many equations. Okay, this is the this one you will get it. So you will get so many equations. Okay, and to find this one, to find now S is hard. So sorry, this is the same as search one. So this one I am writing, I can write in this way also. Okay, what I am doing is I have S, I'll choose one vector A, multiply dot product, and then I'll add E, I'll get one equation. Then I'll do the same thing, I'll get another equation. I'll do the same thing with different value of A and E, another equation. So like this, I'll get many equations. To find S from this equation is a hard. So these both are same basically. Okay, both are same. I'm just writing this in a proper in a cryptographic format. Okay. Okay. Now the decision version. So this LWE has another version, decision version. Now in this one you have two ways to find the A and S. So you have A, this you got it. Okay. So now we can find out in two ways. Oracle one way is the way you have done till now. You choose E, multiply with the AS, dot product with the AS, then add small noise, one equation, one. Then another A, same as AS plus another noise, another one. So A and E are different. So, okay. This way you will get it. You got one. From this one you will get A and this value. Now another way you find out, you have to get another way, another oracle way. You just choose random one, random vector of size n, and because this A is the size of n, and this AS plus E is size of 1, because dot product plus E is 1 Z. So you choose one random vector and one element of Z. Okay. So we have taken the two values. One is computed through proper formula, applying the formula AS plus E. Okay. Another one is taken randomly. Is clear? So we have taken the values in two ways. Oracle one wise, you have to do the formula one, AS plus E. You choose S is there, multiply with the dot product with the vector E, plus add one noise, small noise. And second one, find the random vector of size n and one element of Z. Okay. Now, if I give you these two values, one of these two values, you cannot say that, it's hard to say that the value is result of oracle 1 or the value is result of oracle 2. So it's hard problem. So if someone gives you the value and he tells you that whether that value, that two values are from the oracle 1 or oracle 2, you cannot distinguish. You cannot say that this value is from the oracle 1 or oracle 2. That is a hard problem. That is called decision. You can't decide whether that value, the two values are result of oracle 1 or oracle 2. So this is also a hard problem. This is called the LWE decision hard problem. So this is the decision version of LWE. Okay, this is clear. I hope it is clear. Okay. So this is the part. Okay, so now we'll see the schemes. Okay, so we'll see the schemes. So first scheme was given by the Raghav. Yes, he got the LW hard problem, and then he constructed the LW based public key crypto system. So this is the first one. Okay, so we'll see this part, n cross m. What is the size of that one? So you have to choose one matrix n cross m, or you can say that vectors, m vectors. Okay, that already you've seen. Okay, so now first you have to choose your private key. Okay, everyone has to choose in public key cryptography. Everyone has to choose the private key. The private key will be a vector s, like s1, s2, s3, sn of size, vector of size n. Okay, s1, s2, s3, sn. That is the private key. Now public key will be as you have done previously also. So what you have to do is, as you have done previously, so that same LW, you have s, you have s1, s2, s3, s4, you have taken as a private key, and you do the dot product. You choose a vector a 14, 15, 5, 2, and do the dot product. Okay, that you will get it, and then you add small noise. Okay, so that is, let's say it comes 8. So 8 will be a public key. Maybe let's say this comes out to be 9 or 7, and then you small add the noise 1, that will be 8. So 8 will be your public key. This. So you do this one. So okay, or in the, it is nothing but as you have seen. So this. So or in a matrix format, proper format, you multiply ST with the matrix A, capital A. Capital A is nothing but this collection of these vectors, AIs. So capital A is basically matrix, which is collection of these n vectors, where each of size m. Okay, so this, sorry, m vectors. So where each of size n. Okay, so this is the A, and the E is the noise. E is the noise from the Gaussian distribution. Okay, so this B will be a public key. So B is nothing but same as you see, the B is nothing but your 8. B is nothing but 8 here. Okay, so STA will be the first equation. This is a noise. So B will be your public key. Is clear? So B will be your public key. Okay, so now you want to encrypt. So to encrypt, you need receiver's public key. Let's say receiver's public key is B. So let's say receiver's public key is B. You want to encrypt the message to me, and my public key is B, my private key is S. So what you will do is, you will encrypt the message M using my receiver's public key, that is B. So here you can see the encryption done by bitwise. Okay, first I am doing encrypting 1 bit. That's why I told you the ciphertext blow up. For each bit, for 1 bit, I am encrypting 1 bit. You can see the size of the ciphertext. So now we'll see the size of the ciphertext. So I am encrypting 1 bit. Okay, so 1 bit. So let's say string is, so what you can do is here 1 bit, you to increase this bit, I want to do the following. So choose a string X. Okay, X of size M. Okay, and then what you do is, you find out, this is basically to randomize it. You know, randomize this X is basically to randomize the encryption. You know, to randomize encryption, randomize public key encryption, basically same message, different time, you will get different ciphertext. You are encrypting the same message, but if you encrypt right now, you will get one ciphertext. If you encrypt the same message after 1 hour, you will get another ciphertext. This is called randomized encryption. So this is, X is used for to randomize the encryption, and this security is based on IIS problem. So inhomogeneous. So you see, inhomogeneous integer solution problem, that you see. So there are 2 hard problems are there, LWE and IIS problem. Okay, so this scheme is based on Too hard problem, LWE, IS. So we will see how. So now you choose X. So the X is consists of 0, 1. So the if 0, 1, so size of the X, maximum value of X will be M root M, 1 square, because the maximum value can be if all are 1, 1, 1, 1. All are 1, 1, 1, 1, 1. That is the maximum value. And this X with value M considered to be short. So the M, the value, any vector with value M is considered to be maybe M size of the M is, let's say, 300. So the X will be 300. So that value considered to be short. Okay. So now what you will do is first you multiply these two Xi and Ai. Now Ai is basically your A matrix A summation. So Ax you do it. So A is the public key also. Okay. So Ax you do it. You will get Ax U. Okay. So this U is public. You see this we have to send as a public. So this will be part of the ciphertext. You will see this part. And then what is the first part, U, which is Ax. Then U dash will be the bit which you are encrypting, and encrypting one bit at a time. This part is repeated one bit at a time, and then you multiply Q by 2. Q by 2, the nearest to Q by 2. Okay, and then B public key, B public key, and T transpose, and then you multiply with the X. Okay, so this is the encryption, and then the ciphertext nothing but U and U dash. I didn't write here. The ciphertext is nothing but U and U dash, and U and U dash is sent to the receiver. Okay, so the receiver also, the adversary also knows U and U dash. Is clear? So receiver also knows U and U dash. Okay, so now how to decrypt it? So you know the decryption. You know the decryption here. U and U dash. Now from this U dash we want to find this bit. I have written bit. This bit. This is the message. So I have to find out this bit. So what you can do is, if you subtract from this U dash, if you subtract BTX, okay, if you subtract BTX, you can get this bit into Q by 2. That you can get it. Okay, and from this bit into Q by 2 you can get the bit. So that is the approach. So now what is BTX? Receiver doesn't know the X. Okay, but he knows the U, and from this U he can compute BTX, and this B is public. B is the public key of the receiver. Okay, so how to find out BTX from the U? So what you can do is, you can see what is the B. B is basically STA plus E. You can see this part. So if I multiply here in the U, if I multiply S, because S is a private key. S is the private key of the receiver. I'll multiply this S here, and what I'll get? I'll get somehow, I'll get STAX. This I'll get it, and that is, sorry, so this STA, so I know this one. I'll multiply S here, sorry, I'll multiply S to this U. I'll get this, you see this part B. You do B transpose, you will get A. This I have not written completely here. So A transpose, if you do B transpose, this will be A transpose S, and you multiply X here, this X, A transpose S X, and that you can get from here. You multiply S in the U, you multiply S in U, and subtract from the U dash, and you will get bit into Q by 2. So you will get U dash minus S2U. This you will get it. Okay. Now in this one, if you do the calculations, you will get bit Q by 2, bit into the message bit Q by 2, plus because this is noise, the X also multiplied here, AX. Okay. So now you have to see here, this we didn't get bit. This we have to compute. Bit is either 0 or 1. Now So what you will do is now the output is will be 0 if this is near to 0. So if this is, see, bit equal to 0, this value will be 0, and then this ex, that is the noise. Okay, so what is the algorithm is that if this value is near to 0, then the output will be 0, and if this value is near to q by 2, then output will be 1. Why this one? So if it is 0, then this will be 0, then only ex will be there. Ex is very small, so this value is near to 0. So when this value is near to 0, the output will be 0. When this is 1, then this value will be near to 1, near to q by 2, sorry. And in that time, the bit will be 1. So the decryption algorithm is that if this value is closer to 0, then output will be 0. If this value is closer to 1, then output will be 1. It's clear now? Now, why this will be correct? Because this ex, if it is more than q by 4, because it can be, see, it will give the wrong answer if this ex is more than q by 4. Because if it is more than q by 4, then for 0 it will give you the q by, it will be near to q by 2. Then it will give the wrong answer. For 0 it will give the 1, and for 1 it will give the 0. So this ex has to be less than q by 4. This noise e and x has to be q by 4. Then only this will be the correct, it will give the correct answer. So this is the correctness criteria. Okay, so in the correctness criteria, what we have to show that the ex will be less than q by 4. Okay, so ex has to be less than q by 4. That we have to show. You have to show that probability that this term is greater than q by 4 is negligible. That you have to show. Okay, that you can do. So now I told you the error, the E is Gaussian normal distribution. So you have m normal distributions, each with a standard deviation alpha q and 0. And now if you sum it up, because in worst case you see that all x are 1 1 1. That is the worst case. So you'll have all normal distributions. So then you have sum of the normal distributions. So theorem is that sum of the normal distribution is also normal distribution with mean 0 and variance will be this one. That is the theorem. Okay. So sum of the normal distribution is also a normal distribution with mean 0, and but the variance will change. So variance will be this one, where alpha is this value. This is the formula. Okay. Now the variance will be sigma square, that comes out to be less than q square always. And if you q by 4 roughly comes out to be, if you do the calculations here, q by 4 roughly comes out to be 10 sigma, 10 variance, 10 into variance. Okay, 10 into variance. That comes, so q by 4 value comes out to be 10 sigma. Now you know that in the normal distribution or in the standard normal distribution or Gaussian distribution, probability that, see, in the 99, you know the del graph. I don't have this one, del graph. So from the 99 points, 99 area will be between this mean plus 3 sigma, so mean minus 3 sigma to mean plus 3 sigma, the 99.9 values, the 99.9, the area, the 99.9, the percentage of the area will be between m minus 3 sigma to m plus 3 sigma. Here the q by 4 is 10 sigma. So probability that the value will be very high, more than q by 4, will be very low, will be negligible. Okay, this is the correctness. Is clear? Okay, so this is the correctness criteria. So this shows that. Now if you see the little bit security, I'm not proving security proof here. You can see x is small. The adversary cannot find x. He knows u, he knows a, but he cannot find x because it is a IS problem. IS problem, what it says that you are given ax and that is u, to find sort x, that is m here, is hard. So from ax, from u, it's hard to find x. That is hard. So you can't find x. If the adversary can find x, then you can easily decrypt. Okay, so you can't find x. Okay, and similarly from this part, bt q by 2 plus 1. This is again this is also you can't find the bit. That is common. And now you can see key also. You can see this part key. This is LW hard problem. From this, A is known to 1, B is known to the adversary. You can't find S and E. That is LW hard. Okay, so this scheme is based on two hard problems. That is LW hard problem and IS hard problem. Okay. Now another version is dual version. Dual public key use. So in this case, what they have done is, you see in this case, the LW is used, LW hard problem is used to generate the keys from private key to public key. From this public key, you cannot find private key. That is because of LW hard problem. So you are given B and A, you can't find S. That is because of LW hard problem. Okay, and this to randomize one, this is the IS hard problem. Okay, so now in the another public key crypto system based on LW, what they have done is they are computing public key from private key using IS hard problem, and this to randomize the encryption, they are using LW. So they have changed it. So this part will be here to randomize one, and to compute the public key from the private key, that will be IS problem. Okay, that will see. Rest is same. So now you can see, you choose the sort vector. X is sort of size less than m. The vector is of size less than m. This is sort, considered to be sort. You choose x, and then you find out public key AX. Okay, so the B is the public key, and we know that given B, one cannot find X. That is the IS hard problem. Okay, this IS hard problem is used in the key generation part, and to randomize one, they are using LW hard problem. So now you want to encrypt one bit. Okay, one bit you want to encrypt, and then you want to encrypt one bit. So this is the randomized part. U is the randomized part. You choose S randomly. This while encrypting, this is S is chosen. It's not chosen. It's not constant. Different time it will have different value. Okay, so you compute U, and then you compute U dash this way. Okay, so now you can see this U is the security of U. From this given U, one cannot compute S. That is because of LW hard problem. That is because of LW hard problem. Clear? So that just these hard problems are interchanged. Rest is same. So again, the decryption is same. You do EX, then the probability correctness criteria also same. Okay. So now so this I am just skipping this part. So now just I see, I told you what is the weakness of this. What is the negative part of the latest based public key crypto system? As I have told, it is the ciphertext blow up. For 1 bit of, you see here, 1 bit of encryption. What is the size of the ciphertext? You can see your M of each of M vector of each of size Q, and then this is one value. So you have Q plus roughly for 1 bit only. For one bit, roughly you have Q plus 1 values in the size of ZQ. Let's say Q is let's say Q is roughly will be 300 bits only. Q size of Q will be 300 bits. Okay, and then you need for one to encrypt 1 bit, you need M plus 1 values, each value of 300 bits. That much ciphertext is required. Okay, it's very high. Okay, that is ciphertext blow up. Now, if you want to have size of the public key is also very large. You now see public key. So you have public key X is the private key of size M. This is M, but the public key is very high. You see, each of size Q, n vector of size Q. So n is very high, around to 300. So 300. M is around 2000 something. 300 into M is of, let's say, here this for security requirement, n is roughly around 300, and m is of roughly around 3000, maybe 3000. So the matrix is 300 cross 3000, something like that. Okay, that. So you see here the public key size will be of the vector is a public key is a vector, but each element vector of size n, for each element of size of 300 bits. Okay, this is the case. But if you see the LGML on RSA, the public key of only one value of size 1024 bits. The size is little bit high there, 1024 bits, but only one value. Here, the size is vector of size n. Okay, so n is around, you can say n is around 300. So n is around 300, and the q is roughly also 200 something. Q is also very low. Okay, so 300 into 200. In the RSA case, only 1200 bits. The public key size is 1024 bits, but here it is 300 into 200. That is very large. So public key size is very large. Okay, so this is. So I think I should stop here. So if you, time is okay. Time is over. So so if you have 10 minutes are there. So if you have any questions, so now you can ask me. So I didn't discuss the security part, but that we can see. Okay. So in this schemes, if you have any queries, you can ask me. If you have any general inquiry, if you have any queries in cryptography, also most welcome. Any queries?
Does anyone have any doubts?
Hello, sir.
Yeah.
Can you hear me?
Yeah, I can hear you.
Sir, this method and the previous LW method, they seem similar. I just can't tell the difference apart.
Yeah, it's similar only. That's why I'm telling you. It's a dual part. It's a dual public key crypto system under LW assumption. This is given by GPB, three scientists. The last one is V. Vaikuntanatham. He's from Kerala also. Manoj Vaikuntanatham. He's from Kerala. He is well known in this lattice-based cryptography. So this is similar only. Only the thing is, you see, LWE, they are using two hard problems. One hard problem they are using for to find public key. Another hard problem they are using to randomize the encryption. That is here. Just they have changed it. Okay. Just they have changed it. Nothing. Rest are similar. Everything is same. Why this dual is useful? Why they have given the dual? From this dual GPP they have given the dual. They have done the identity-based crypto system. So when you have IIT based crypto system, I hope if you know study this part, the IIT based crypto systems are basically the dual, similar to the dual one. So otherwise dual is like previous one. So these IIT based crypto systems, they are also, this is given by the GPB only. So the same thing I have given. Yeah. Yeah. So LW the same. So the same thing as dual public key system. Okay. So this is same as dual public system. Only thing is IIT. Okay. So both are same. Both are, you can say both are same. Only that the key generation part and randomized part are, the hard problems are swapped. Hard problems are swapped only.
Okay, sir. Thank you.
Okay. Whatever. Yeah. Any questions? If there is no questions, then I can.
So there are no more questions.
Okay.
Thank you, sir, for this descriptive session. We thank you for sparing time from your busy schedule and being here with us today.